Hi, thank you for the introduction, James. Um, so today I am really excited to talk to you all about some of the first stars in the universe and why they are so important in understanding how we got to the universe that we know today. So to talk the lights down, we can. Nope. Better? Okay. Okay, cool. We'll go with that. All right. So to understand the first stars in the universe, we need to start a little closer to home and understand where we're situated today. So I want to start with our home, the Earth. Our Earth is remarkable for a lot of reasons. We exist on our Earth, which means that it must be special in some way. None of the other planets in our solar system have life. It's a beautiful planet, but is it typical of the planets in our universe? So to answer that question, we should think about what the Earth is made of. So the Earth is made of a variety of elements, compounds, but some of the most common are iron, oxygen, silicon, carbon, and lots of other metals. A note here that astronomers use the word metal to mean everything except for hydrogen and helium. So throughout this talk, when I say metal, I mean any element on the periodic table that is heavier than hydrogen and helium gas. In this case, the Earth has lots of metals in the astronomy sense, but also lots of metals in the way that we normally think about a metal. And so the Earth is really varied in terms of its chemical makeup. And obviously we know this because we live here, right? We can pick up the rocks under our feet, and we can take samples from our atmosphere, we can study lava from volcanic eruptions to learn about the mantle underneath the Earth's crusts. And so we have a really good sense of all of the elements that make up our Earth. But is the Earth typical of all of the other things in the universe? To answer that question, let's go a little further out to our sun, the nearest star. This is our sun. And our sun has a composition that's very different from the Earth. The sun is primarily made of hydrogen. It also has substantial amounts of helium. And then it has trace amounts of everything else that we call metals. And this chemical makeup of the sun is actually not trivial. We didn't know what the sun was made of until about 100 years ago. And that's because, unlike the Earth, we can't just pick up a piece of the sun and test it in a lab, right? So it's really hard to figure out what it's made of. So the way that we figure out what the sun is made of is by using the only thing that we do have access to, which is the sun's light. So we do this by looking at something called its spectrum. The way that this works is that if we have a prism like this can be literally just a piece of glass shaped like a pyramid, works as a prism. If sunlight goes into the prism, just normal white sunlight, just simply because of the geometry of the prism, the light will come out the other side decomposed into all of its wavelengths that make up that light. And so we get a rainbow. This is exactly how rainbows are formed. Like when we see a rainbow in the sky, it's because this is happening with water droplets in the atmosphere. And so we can see, using just a prism like this, that the sun's light is made up of light of all different wavelengths. So we have the whole rainbow of the colors of light that our eyes can see, plus we have wavelengths of light that our eyes can't see. So here we go at the top, we have longer wavelengths of light, which are lower energy, and that would be things like radio waves, microwaves, and infrared light. And then we go into the red light that our eyes can see all the way through the rainbow to bluish purple light, and then smaller wavelength, higher energy light, like ultraviolet, and then things like X-rays. You can remember this because the higher energy types of light, like ultraviolet and X-rays, we recognize those things as things that can hurt us, right? They have so much energy that they can disrupt our bodily processes. That's why ultraviolet light from the sun can give you a sunburn, and we need to protect ourselves from X-rays when we go to the doctor. So this is how we can tell what all of the components of light that the sun contains are. But how does the sun even create this light in the first place? Well, that's because of a process called fusion. So very simply, fusion works by taking lighter elements mostly hydrogen in our sun, and turning them into heavier elements plus energy. So in our sun, this works by taking hydrogen and turning it into helium. Fusion can only happen when something is really hot and really, really dense. So at the very center of our sun, it's hot enough and dense enough that there's a ton of hydrogen atoms going around really, really fast, and sometimes they bump into each other. And if 4 of them bump into each other, they will smash together and form helium. And that reaction creates energy in the form of light. And so that's why the sun shines, is because you get this extra energy coming out of this fusion reaction. This doesn't have to happen with hydrogen and helium. It can happen with really any lighter elements going to heavier elements up to a point of the periodic table. So for example, helium atoms can fuse together into things like carbon and oxygen. But in the sun, this is the way that this works. And so that's where our light comes from. And then the way that we can use that light to learn about the sun is that if we think of this as the sun, at the very center, that's where fusion occurs. The light is created in that fusion reaction, and then it travels outward out of the sun and hits our telescopes. And then we can take that light when it hits the telescope, put it through a little pyramid like the one that we saw on the previous slide, and we get what's called a spectrum. So this little rainbow here is like what we saw on the previous slide. That's one way of looking at the spectrum, basically just all of the different wavelengths of light from the visible here down to infrared and ultraviolet on the 2 ends. You can also look at this spectrum in terms of this little plot here. It's very similar to the rainbow above. On the x-axis, we have wavelength. So that's exactly the same as this. You've got blue over here on the left side and red over here on the right side. And then the y-axis is brightness. So that's just how much of each wavelength of light is the sun emitting. So you can see this is approximately what the sun spectrum looks like. You can see the sun emits a lot of light in sort of bluish green wavelengths and less light in redder wavelengths. And that kind of tapers off on both ends. So this tells us some things about the fusion that's occurring at the center of the sun. But we still haven't answered that question of how we know what the sun is made of. And the way we answer that is because this picture isn't quite as simple as I've made it look here. In the atmosphere of the sun, on the kind of outer edges of the sun, there's more stuff, right? There's all of the things that the sun is made of. So that's going to be hydrogen, helium, and some heavier elements that I'm calling metals. And as the light that is created in the center of the sun travels outward, it will interact with all of the things around the edge of the sun, right? So that light will travel outward, and it might bump into a helium atom in the sun's atmosphere before continuing on to our telescopes. And what that does to the spectrum that we see is it creates what's called an absorption spectrum. Every element has a unique fingerprint of specific wavelengths of light that it can emit or absorb. So, for example, perhaps hydrogen absorbs this specific wavelength of sort of yellow-orangish light. That means that all of the light created in the center of the sun, any of that light that interacts with hydrogen at the surface of the sun, that specific yellowish wavelength might get absorbed, then it won't reach our telescope. So what we end up with, instead of a full rainbow, is a rainbow with little gaps in it. And those gaps tell us what elements are in the sun's atmosphere. If we know what the fingerprint of hydrogen looks like, and we know what the fingerprint of helium looks like, we can then identify it as a gap in this little rainbow spectrum. We can do the same thing with the version of the plot that we see down here. Instead of a little black band, we just see that gap as a dip in brightness at that specific wavelength. And so this tells us what the sun is made of, right? We can look at the sun spectrum. Sorry, let me go back here. We can look at the sun spectrum and we can, oops, that's okay. We can look at the sun spectrum and we can see exactly all of the components that it's made of, and we can identify all of the elements. I do want to go back here really quickly. One note, so we discussed these absorption spectrums, right, where you get a little black line where you're missing a wavelength of light. every atom, every element on the periodic table can also do the opposite, where in different conditions, it can also emit that wavelength of light. So that fingerprint pattern can be either in absorption or in emission. And those two patterns are identical. It's just like, a black and white version turning into a white and black version, basically, depending on the conditions of the gas, how hot it is and such. So depending on the conditions, we will either see a rainbow with lines missing, or we will see just those exact lines. And so, yeah, this is how we get to the sun's overall spectrum, which looks like this. Up here is the same sort of rainbow color bar that we've looked at before. And you can see all of those black bands correspond to little dips in the overall plot of the brightness of the sun at different wavelengths. So like this black band here in the red corresponds to this big dip in brightness right there, which is, according to this, a feature of oxygen. And so based on this, we can tell what the sun is made of and how much of each element is in the sun. And from a lot of very detailed studies like this, we have figured out that the sun is about 71% hydrogen, 27% helium, and 2% everything else. So that's what our sun is like, very different from our Earth. The other rocky planets in our solar system are much more similar to the Earth. The other gas planets in our solar system are closer to the sun than they are to the Earth in terms of their chemical makeup. And that kind of gives us an overall picture of the solar system. But our solar system is not alone in our universe. There are billions of stars in our Milky Way, and those stars are generally very similar to the sun. They will have 70 to 75-ish% of hydrogen, about 25-ish% helium, and a couple percent of everything else. A lot of those stars probably have planets. Some of those planets might be like the Earth. Some of them might be gas giants like Jupiter and Saturn. But our Milky Way is full. This is a top-down artist's rendition of what our Milky Way galaxy probably looks like. Note that we can't get this view in a real picture because we're inside the Milky Way, and so we can't look at it top-down. The sun and the Earth are right about there, about halfway from the center in one of the spiral arms. And at the center, we call the center of the Milky Way the galactic center, sort of self-explanatory name there. And in the galactic center, we not only have stars and planets like we do in our own solar neighborhood, but we also have a huge supermassive black hole. The one at the center of our Milky Way is called Sagittarius A star, and this is a picture of it. You might have seen this in the news a couple of years ago. This picture was a really big deal in astronomy. It's one of the first actual pictures of a black hole that we've ever taken. And what you're looking at here is at the very center in the sort of dark splotch, that's where the black hole actually is. Black holes don't emit any light, and so we can't actually see them. So what we're seeing here is the absence of other stuff in the center there. That's the black hole. And the ring of lit material around it is a ring of hot gas and dust that emits some radiation just because it's hot, orbiting around the black hole. And so that's how we can see where the black hole is. And this black hole, I said, is massive. It's millions of times as massive as our sun. And so together, this is sort of a picture of what our galaxy looks like. Supermassive black hole at the center, surrounded by billions of stars, many of which have planetary systems just like our own. And our Milky Way is also not alone in the universe. There are trillions of galaxies in our universe, many of which look very similar to our Milky Way. All of these galaxies contain millions, billions, maybe even trillions of stars. Many of those stars probably have planets. And almost all of these galaxies also have supermassive black holes at their centers. And so our universe is hugely varied. There's a huge variety of structures present across our whole universe. But it didn't always look like this. In fact, at the beginning of the universe, after the Big Bang, it looked more like this. It was just dark. There was nothing there. Or I guess more accurately, it looked sort of like this. It was dark, yes, but it was filled with hydrogen and helium gas. The Big Bang created hydrogen and helium, and that's all. So those were the only elements of the periodic table that existed right after the Big Bang. And all of that gas was floating around in a sort of hot soup. You can think of it sort of like the oceans, just kind of a big, dense, hot soup of gas with no structure. And so the question is, how did we get from that in the early universe to the huge variety of structure that we see in our universe today? So if we imagine that this is that hot soup of gas in the early universe, it's pretty much the same everywhere, except not quite. It is slightly denser in some areas than others, just because of random chance. As you can see in this picture, maybe it's a little bit denser over here and a little less dense over here. If you imagine this is sort of a density map of that just soup of gas. And so as time went on in the early universe, those slightly dense regions like this one would start to accumulate a little bit more density. They would become slightly gravitationally bound. And so more of the gas would gravitate toward those overdense regions. And that kept happening as the universe grew, as time went on, until those overdense regions became dense enough and therefore hot enough that fusion could start. And as soon as fusion started, they started emitting light. And those were the first stars. As soon as you have fusion creating light, you have a star, basically. So the first stars were created just from this soup of gas that condensed down to hot enough in little areas to start emitting light. And this set our universe off in the path that it has gone, that it has followed until today. So we're going to talk a little bit more about how that happened. So these first stars were really different from the stars that we can see in our sky today. They're very different from our sun. And this is primarily due to their chemical makeup. So as I said, in the early universe, the Big Bang only created hydrogen and helium. And so those were the only two elements available to make the first stars. And so the first stars had the exact same chemical abundances as the Big Bang created, which was about 75% hydrogen and 25% helium. And you'll note that's a little different than our sun, which is over here, which we've said has about 71% hydrogen, 27% helium, and 2% heavier elements. The important difference here is those heavier elements. And you might not think that 2% is a lot. 2% is, in fact, not very much of the whole total. But that 2% is super important in determining the fate of that star and how it lives its life. This is due to a lot of complicated gas physics, but basically, heavier elements or metals have the ability to stabilize gas. They cause it to collapse differently. And so the fact that these first stars didn't have any heavier metals means that they lived very different lives from our sun. So first of all, the first stars were massive. So you can see here, this is an image to scale. The sun is here. That's how big the sun is. Aldebaran is one of the largest stars in our local universe, nearby to us. It's what's called a red giant star, and it's really big compared to the sun. But here at the bottom, you can see just how big the first stars were. This first generation of stars that were formed just out of hydrogen and helium were huge. Now, we don't know exactly how big they were because we don't quite understand the details of how the lack of metals changed the way that these stars operated. We think they were probably somewhere between tens to thousands of times as massive as the sun. They were probably a range of masses, but they could have been up to thousands of times as massive as the sun, and therefore much, much bigger. Partially because of that, they were also far hotter. So our sun has a surface temperature of about 6,000 Kelvin. It's sort of average for a star. The hottest stars in our nearby universe can have surface temperatures up to about 40,000 Kelvin. So that's a lot hotter. But this scale is exponential. And the first stars were far more massive, far bigger than these stars in our nearby universe, which means that they were exponentially hotter. So these stars burned incredibly, incredibly hot. And then partially because of that, because of how hot they were also very short-lived. So this plot here shows on the x-axis the mass of a star, and on the y-axis, its lifetime. So our sun is right here. It has a mass of 1 sun, and it has a lifetime of about 10 billion years. All the way over here, we have a star that's twice as massive as the sun. And you can see they live for only about 1/5 as long. So again, this is an exponentially decaying relationship. So if a star only twice as massive as the sun lives for 1/5 as long, then stars hundreds or thousands of times as massive as the sun would live for a tiny fraction of the sun's life. So whereas the sun will live for 10 billion years, these first stars probably only lived for maybe 10 million years, or 1/1000th as long. So all of these things make the first stars really, really different from stars like our sun. In summary, they were made of only hydrogen and helium. And because of that fact, they were incredibly massive, they were very hot, and they were short-lived. And when you put all of these traits together, it causes a very different end of life than stars in our local universe. So when these first stars died, because of all of these traits, they would have exploded in some of the largest explosions in the universe. These explosions are called supernovae, and they happen nearby as well. Stars in our Milky Way explode in supernova, particularly the more massive stars in our nearby universe end their lives as a supernova. And what a supernova is basically when a star can no longer have fusion in its core, when it's run out of things like hydrogen to be able to fuse, then the core will implode, or it will collapse inward just due to gravity. And so you'll get the center of the star collapsing really quickly. And that collapse causes a shock wave that radiates outward. And that outward shock wave causes an explosion, where all of the outer layers of the star, all of the orangish red here, will get blasted outward from the star. And so what you're left with is a very compact thing at the center from this implosion of the core, plus a bunch of hot gas around the outside from the explosion of the exterior of the star. So this happens in our universe today, but the explosions from that first generation of stars would have looked really different from the ones today. And again, that's because those first stars looked different from stars today. So in particular, these first supernova explosions would have created some of the things that have led our universe to what it looks like today. So the explosion of the outer parts of those stars would have been really hot, right? Super energetic. You've got a huge explosion, like you're blowing up probably billions of tons of bombs all around the outside of the star. And because it's so hot and energetic, those are the conditions for fusion. And so you'd get a really quick blast of fusion that would create heavier elements as the star explodes. So as the star explodes, you'd create things like iron, things like oxygen, things like silicon, things like carbon, which are all of the things that make up the Earth. And so these explosions would create these metals that then can go on and form into new stars and things like planets. This cycle continues, right? So all of this gas that gets blasted off will form into new stars, and then those new stars will go through their lifetimes and do the same thing. And so over time, this creates the universe that we know today, where you can have planets like the Earth that are made of just these heavier things, or primarily these heavier elements. You create all of these heavier elements in these supernova explosions. Without this first set of supernova explosions, we never would have been able to have stable, long-lived stars that have led to the universe that we have now. Meanwhile, the implosion of the center of these stars would have created black holes. This, again, is the picture of the black hole at the center of the Milky Way. The black holes at the centers of these first stars would not have quite looked like this. they would have been a lot smaller. But these black holes, which as of now are just theorized, we've never actually observed these black holes that would have been created from the first stars exploding. They have the potential to solve a really challenging problem in astronomy right now, which is something called the black hole mass gap. So this is a scale of the mass of black holes on the x-axis here. So down here, we have what we call stellar mass black holes. These are black holes that have a mass of about the sun's mass up to about 100 times the mass of the sun. And these are the black holes that are created when massive stars die. You get a black hole like that. Then on the very other end of the scale, we have supermassive black holes, like the one at the center of our Milky Way. And those black holes can be hundreds of thousands or millions or tens of millions times as massive as our sun. And then you have this whole mass range in the middle. And we've never seen a black hole in that mass range. We don't know how they could be formed, and we've never observed one, which is sort of weird because we know that these smaller black holes exist, and we know that these large black holes exist. We don't know how you actually form these large black holes, but it wouldn't be crazy to think that smaller black holes could merge together to form larger black holes. We know that black hole mergers can happen. But we've never seen any black holes in this huge middle mass range. So this is a really big problem in black hole science in general. And the first stars are potentially a way to partially solve this problem. This is still theorized. We haven't observed this. But if the first stars were 1,000 times as massive as our sun, they could have created, when they died, a black hole in this intermediate mass range. And if the first stars lived really fast, died really quickly, and died in large groups or clusters of stars, which we think they did, then you could have created a lot of these intermediate mass black holes, which could then potentially merge together to form the beginnings of supermassive black holes that we have at the center of all of the galaxies in our universe today. So we're not sure if this is exactly how things happened in the early universe, but it's one of the better theories that we have as to how you could form supermassive black holes. And so potentially, the first generation of stars could also solve that problem. So the first generation of stars, we know they looked broadly different from the stars in our universe today. And we know that they have potentially started to kind of set our universe on the path to what we see around us today. But how do we actually know any of this, right? These stars lived billions of years ago in the early universe, and they died really fast. So there aren't any of them around to study. So how do we actually learn about them? There are two main methods that astronomers are using today. The first is due to the fact that all of the gas that was exploded off of those stars in their supernova explosions floated around in the universe for a while and later formed a new generation of stars. All stars form from the gas that had been in previous stars. That's not special, but a star like our sun, the gas that formed our sun, has probably been recycled maybe 10 times, maybe more, many, many times. And so it's hard to pick out what any one of those supernova explosions might have looked like. But if we can find stars in our nearby universe that directly formed from the gas from the first stars, we can do exactly what we did with our sun at the beginning of this talk, look at their spectra, and learn about the explosions that led to their formation. We can learn about those first supernova. We can learn about how they're different from the supernova in our local universe, and that can tell us maybe how the first stars were different from the stars in our nearby universe. So this is sort of generally how we might do this. So we're back to spectra here. This is a little piece of our sun spectra. This is the same plot that we were looking at before, where we have wavelength on the bottom and brightness along the y-axis. And if you remember, all of the little dips here are absorption lines. A couple of them are labeled. Fe means iron. So this absorption feature right here, this one right here, and this one right here all correspond to iron. They're each like one little piece of iron's fingerprint. And this one right here is nickel. And you can see there are tons of other absorption features along this. There's just tons of little dips in the sun's spectrum corresponding to different elements or even molecules that are in the sun's atmosphere. So most stars near us look like this. This is a star that was formed from gas from countless supernova explosions. But this star here, which looks like a few stars that we've seen in the outer reaches of our Milky Way, this is what we call a metal poor star, which means it doesn't have a lot of metals in it. You can see it still has this, these, I guess, 3 iron features and the 1 nickel feature there, but it doesn't really have anything else in between them. There's no other dips in the star's spectrum. That indicates that there are less metals in this star than there are in our sun. So our sun, we said, has about 2% metals. This star maybe has 0.2% metals, or maybe 0.02% metals. And then if we kind of work this backwards, maybe we could see a star like this. This star has only 2 of the 3 iron features. The one over here, it's missing, and it has no nickel at all. This star might be what we call a second generation star, which would be a star that formed directly out of the gas from the death of a first generation star. So this star has only a little bit of things other than hydrogen and helium because it formed mostly from the hydrogen and helium that the Big Bang formed, plus a little bit of extra stuff that was formed in that first supernova of the first stars in the universe. And then if we just kind of bring this to its logical conclusion, this is what a first generation star spectrum would look like. It has absolutely nothing. There's nothing in it except for hydrogen and helium. It has no other absorption lines. And these stars we will not be able to see because, at least not in our Milky Way, because they're all dead. They've all exploded billions of years ago. So if we look at some data over here, this is data from our best example of what might be a second generation star. Up here, we have just sort of a normal metal poor star for comparison. We again can see these 3 iron features and the 1 nickel feature. This is a larger chunk of the spectrum, so you can see another iron absorption line over there. And then we can compare that to the star that this paper discovered down here, which is a candidate second generation star. And you can see it's missing almost everything. It has this 1 absorption feature over here, which is a type of carbon, but it doesn't have any iron or nickel. And what this can tell us, if this really is a second generation star, is that the first supernova, when those first stars died, maybe they didn't make any iron or any nickel, which would be weird because when stars in our nearby universe die, they make a lot of iron specifically. They make a decent amount of nickel too. And so that tells us that those first explosions were very different from the explosions in our universe today. And that indicates more differences about those first stars. So this is a really exciting area of research. This is the kind of thing where we need better spectra of the stars in our Milky Way. So better telescopes are working on this. This is not what I do, but it's very interesting. There are some other grad students at U of T working on this kind of thing. The other method of looking for the first stars is actually just to directly look for them. To look back in time into the beginning of the universe and try to see these stars as they existed in the beginning of the universe. That might seem impossible, but in astronomy, we can do the impossible, and we can actually maybe do this. And this is because of a really sort of simple but very, very important fact in astronomy, which is that light travels at a constant and finite speed. And what this means is that it takes light time to move. So in our own solar system, it takes light about 8 minutes to get from the sun to the Earth. And what that means is that if the sun were suddenly to blink out of existence, we wouldn't know for 8 minutes. Because for the next 8 minutes, the light that we see was already emitted from the sun before it disappeared. So we're looking at the sun as it looked 8 minutes ago. If we go out to the overall view of the Milky Way, it takes light about 26,000 years to get from the center of the Milky Way to the Earth. which again means that we're currently looking at the center of the Milky Way as it looked 26,000 years ago. And if something is happening in the center of the Milky Way right now, we wouldn't know about it for 26,000 years. Scales in astronomy are huge, and so this is actually pretty nearby for astronomers. If we think about galaxies and all of the galaxies in our universe, we see light from these galaxies as they looked millions or even billions of years ago. The universe is about 13.8 billion years old, and galaxies have existed for at least maybe 13 billion of those years, maybe pushing up a little on that. And so we see these galaxies as they looked anywhere from, now in our own universe or in our own galaxy out to about 13 billion years ago for the farthest away galaxies. So to get a better sense of what this sort of looks like when you're doing extragalactic research, let's zoom into a couple galaxies here. So this one here in this little box, to zoom in, this galaxy in terms of extragalactic astronomy is actually pretty close to us. It looks small, but you can see it sort of looks like our Milky Way. It has this disk with sort of a bright center here, kind of like our Milky Way does. So this galaxy, I would say we're seeing maybe a couple 100 million years ago, maybe 1 billion or 2 billion years ago. So it's far away, but not all that far away in terms of the age of the universe. So let's look at a galaxy that's farther away and older. So if we zoom into this teeny little dot over here, this is also a galaxy, this little red dot. And that galaxy is really, really far away. It's probably maybe 12 billion years in the past, which means that this galaxy probably, we're seeing it as it looked, I don't know, a couple, maybe 1 or 2 billion years after the Big Bang. And it's really hard to see galaxies like that. It's a lot easier to see galaxies that are closer to us. Partially, that's just because if you take a light source and you move it farther away from you, it's going to appear smaller and dimmer. And then also because galaxies in the early universe were intrinsically smaller and dimmer. Over time, galaxies grow, and so they get brighter. And so when we're looking back in time in the universe, or really far away from us, we sort of have all of this working against us. So it's really hard to see early galaxies. And so trying to look for the first stars directly in the first galaxies of the universe was sort of futile until just a couple of years ago when the James Webb Space Telescope launched. And some of the other astronomers in the room might disagree with me here, but I would say that the James Webb Space Telescope is the most powerful telescope humans have ever built. It can see further back in time than any other telescope and with a much better resolution. It's a really, really incredible instrument and has entirely transformed the field of extragalactic astronomy. And so using the James Webb Space Telescope, we're finally able to search for signatures of the first stars in some of the first galaxies. So I'm going to briefly talk about one of these signatures that we look for. This signature is the presence of a specific emission line of helium. So we mentioned at the beginning that emission lines are sort of the exact same but opposite of absorption lines, where an element can emit a very specific wavelength. And so there's a specific wavelength that helium emits that's special because it takes a lot of energy to force helium to emit this wavelength. And there aren't that many things in the universe that have enough energy to kind of give that energy to helium to allow it to emit that wavelength. The first stars would have been hot enough to do it, not much else in the universe. So if we can see the specific emission line of helium, it's a really good indication that some of the first stars are what are powering that emission line. And so this is what we're trying to do. Currently, there are 2 candidates for this that are decent, I would say not confirmed yet. This is one of them. The galaxy is where this pointer is right here. It's this little dot, that tiny little dot at the center of this image is this galaxy. It's one of the earliest galaxies in the universe that we've been able to see. And this is its spectrum. This looks like a mess, I know, compared to the ones that we've been looking at. It's really hard to see galaxies that are so faint and so far away. So just kind of most of what's in the spectrum is noise, not absorption or emission lines. So you just kind of have to imagine a smooth line that sort of follows the shape of this general spectrum. We have the same exact axes that we had before, wavelengths down here, brightness over here. And then we have this purple line right here where we would expect to see this helium feature. And you can see there's like a little bit of a bump here. You know, there's a bit of a peak that maybe you could say is an emission line, but I would say it's barely above the noise, so maybe not. But if we look at the version of this spectrum that's like the rainbows that we were looking at before, that's this one here with this little inset over here. You can imagine this as the rainbow. You can imagine blue light over here and red light over on this end. You can see the galaxy in emission, so it's lighting up this spectrum. And you can see it's pretty bright over here, and then it gets a little bit dimmer, and then it gets bright again. And that pixel of brightness corresponds to this exact wavelength where we would expect that helium feature. So that's why this is a really good candidate galaxy that might actually have that helium emission that corresponds to the first generation of stars, which means that there might be some of the first generation of stars that are made only of hydrogen and helium in this little teeny galaxy. I would say we need better data to say for sure, but it's a candidate for now. And this is the kind of research that I do. So I work in a Canadian collaboration called CNUCS, the Canadian Nearest Unbiased Cluster Survey. And this is a JWST, James Webb collaboration, based here in Canada. And we have data sort of like the images that we've been looking at this whole talk. And different people in the collaboration are looking for different things. One of the things that I'm looking for is helium features like that. And I found this galaxy. So this is the little galaxy. It sort of has 3 little clumps in it. We don't really know what that is. And this galaxy exists about 13.1 billion years ago, which is about 500 million years after the Big Bang. So it's a really, really early galaxy, one of the first, I guess, in the sort of first generation of galaxies that formed after the Big Bang. And here we have the same axes that we had on all of our spectrum. We have wavelength over here and brightness over here. But you'll notice we don't actually have a spectrum. So the data that we have is not spectral data, but something called photometry, which you can think of as just if you take individual points from that spectrum. So each of these points is how bright the galaxy is in a little range of wavelengths right around where that point is. So like this one would be sort of this whole little range of wavelengths. This one is this little range of wavelengths. And so it doesn't give us as much information as the spectrum does, but it's a lot easier and less expensive to get this data, so we have more of it. And so to make conclusions from this, the way that we would from a spectrum, we need to kind of guess what the spectrum would look like. So it's sort of just a game of connect the dots, right? So that's kind of how you would connect all of these dots to make a continuous spectrum here. And we can also use what we know about what these galaxies should have looked like to make educated guesses about what this should look like. But you'll notice there's one big outlier here. This point, it has a large error bar, but it is definitely above this spectrum that I've drawn here in blue. And wouldn't you know, that's right where we would expect that helium emission line to be. So potentially, if this is real, maybe the spectrum doesn't look like this blue line. Maybe it looks like this. Very similar, but with a big spike right there so that the spectrum matches up with this data point there, right at the wavelength of helium-2, which would be helium-2 emission. If this is true, if this spectrum does look like this pink line, then that would be really, really good evidence that there's helium-2 emission in this galaxy, and therefore there's probably some of the first generation of stars in this galaxy, some stars that are only made of hydrogen and helium. But we can't really say that from just this data. We really need a full spectrum like the one we were just looking at. Thankfully, we are getting one of those in May, so that's very exciting. Yeah, it's really coming up soon, and I'm holding my breath waiting. And so in just a couple of months, we will know if this is real or not. If it is real, that's going to be very, very exciting for all of us. If not, that's too bad. We'll keep looking. But this is a really exciting time in this area of research. New discoveries like this are happening really frequently now in the past couple of years, now that the James Webb Space Telescope is operational. And so now we not only have those stars that we were just looking at, that can give us a hint as to what the first explosions of the first stars looked like, but we're also now finally able to maybe see some of these stars directly, which means that we can attack this problem from two different angles and learn a ton about what these stars might have looked like when they lived and then also when they died, which can help us piece together how we get from that early universe of a hot soup of gas to all of the huge structures that we have in our universe today. All of the planets like the Earth, and the stars like our sun, and the galaxies like our Milky Way. And so, yeah, I hope I've convinced you all that this is a really exciting time to be in this field, and also that this is a really exciting and important thing to study. Yeah, and so happy to take any questions that people have. Thank you. Lights, okay. Yeah. Yeah, so the question is, how do you isolate something so tiny to say if it came from a star or a galaxy? So basically what we do, it depends on whether we're getting a spectrum of the object or the photometry, like the images of the object. But basically what we can do, like on a picture like this, is we have algorithms that identify point sources based on something called a point spread function, which is just basically how the detector detects light that is a point source. And so we have these algorithms that will look at something like this and will like detect that these are three separate blobs and can estimate whether it thinks that those three blobs are all related to the same object or not. And then at each pixel in this object, we will have a brightness or an intensity. It's sort of the same way that like a phone camera works for imaging, that at each pixel you have a brightness. And so you can just isolate each individual pixel and look at the brightness. And then if you want the brightness of the entire galaxy, you can just add up all the pixels. Yeah. Yeah, great question. So you would get absorption when you have a cool gas that is backlit with light, because the backlit light will come through that cool gas and the cool gas can absorb it. And you would get emission when you have hot gas that is not being backlit, because the hot gas will emit energy or light. Yeah, in the background. That's a really good question. Okay, so the question was, where for stars where the iron core implodes, is that how you get iron, basically? Is that how you spew out iron into the universe? And the answer is sort of, mostly not actually. So the core of the star where you get iron from fusion will all implode and will turn into the black hole or some other type of compact object. And the only part of the star that will end up exploding and spewing gas out will be all of the outer parts of the star, which are still going to be mostly hydrogen and helium. And the reason that we get so much iron from explosions like that is because in the moment of the explosion, you get a ton of fusion just for a minute. And all of that will create a bunch more iron. Yeah, it's a really good question. Yeah. Mhm. Okay, so the question was, how do we know that the first stars were so massive, and how much do we trust our models of the stars and supernova explosions? We know that they were definitely massive because metals impact gas fragmentation, and we know that not having metals means that gas will not fragment as much, and so it will collapse in much larger clumps. Um, our models of the supernova explosions and exactly how big those clumps will be are really bad. You get things anywhere from, masses ranging from the mass of the sun to 50 times the mass of the sun up to thousands of times. The models like really do not agree, which is why we really need data. I think we need observations to constrain some of those models. Yeah. The time scale of the first stars. Yeah, so we think that the first stars would have formed. Well, we don't fully know because we don't have any observational data because we've never seen them. We have bookends, basically. We know that there were galaxies as early as 300 to 400,000 years after the Big Bang. That's like the earliest galaxies that we've seen with James Webb. And so there must have been stars a little bit before that, but the stars lived so quickly and died so quickly that it might not have been that much before that. So I would say anywhere on the time scale of like 200,000 to 400,000 years after the Big Bang, but it's not super well constrained. Yeah.
So our sun going to become a black hole?
Our sun is not going to become a black hole. So only the most massive stars become black holes. Less massive stars, like our sun, won't even have a supernova explosion. They will end their lives in something called a planetary nebula, where basically all of the outer layers of gas just sort of float away into space very gently. And the core of our sun will become something called a white dwarf, which is simply just a hot ball of mostly carbon and oxygen that will slowly cool off for billions of years. Okay, one more question. We'll go right next to you. Yeah. Yeah.
What does it mean to learn from that origin based on the trace of something that was but it's no longer?
What does it mean to learn from the yeah. Yeah, so yeah, the question was, what does it mean to learn from like the remnants or the traces of something that is no longer alive, like these first stars? I think we will never know everything about the first stars, right? Because we'll never be able, I think, regardless of how good our telescopes get, we're not going to be able to see individual stars in the early universe if that's what a whole galaxy looks like. But I think we can learn enough to have a much better understanding of how we got from just hydrogen and helium to everything else. I think what we really need, as some other people have asked about like the models that we have, our models are really, really poorly constrained. And I think if we can learn just enough from seeing traces of these first stars to be able to constrain those models, then the models will be able to do a lot better in predicting tons of other things in other areas of astronomy, which will be really, really helpful. Okay, I guess that's it. But please, if anybody else still has questions, I will stick around afterwards to answer them.